All right, so let's take a look at the warm-up. The warm-up is one of the questions from the homework for section 1.3. I got a lot of questions about this one and maybe one other homework problem, so I want to make sure we kind of go through it in detail. So even if you did this and didn't have a question, a couple of numbers are different, so we can definitely go through it. All right, so we have an initial value problem. I have a differential equation, my initial condition. I want to solve the differential equation. I'm going to use separation of variables. So in this case, that x prime is really dx dt. And separate the variables, I'll divide both sides by x, and I'll multiply both sides by dt. I'll get 1 over x dx is equal to 1 over 1 plus 2t dt. And I integrate both sides. On the left, I get the natural log of the absolute value of x, natural log of the absolute value of 1 plus 2t times what? Factor of 1/2. So number one common mistake is forgetting that 1/2. Right, if that 1/2 isn't there, let's get rid of it for a second. How do we check our work after we do an integral? We can take the derivative and we should get back to the integrand. If I just have that natural log, I'm taking the derivative. I take the derivative of natural log of 1 plus 2t, which is 1 over 1 plus 2t times the derivative of the inside function. And if that chain rule kicks in with x a factor of 2, that I don't want to be there. Okay? So the 1/2 is basically killing that extra factor of 2. More formally, if you did a u substitution and let u equal 1 plus 2t, you'd also get that factor of 1/2. We really want you to be able to kind of write that guy out. But don't forget that factor. Any questions there? All right, now I take the exponential of both sides. Plus c. Got to make sure I do my plus c right away. So I got to make sure I do it before I take the exponential. That's common mistake number 2. Not bringing in your constant on the right time. Make sure you bring it in as soon as you do the integration. Now I'm taking the integral, the exponential of both sides. I get e to the natural log of the absolute value of x, e raised to the all of that right-hand side. So I have 1/2 natural log of 1 plus 2t plus some constant. All right. On the left, I know how to handle the left because I have properties, and one of my properties is that e to the natural log of x is the same thing as the natural log of e to the x is the same thing as x. Okay? It's just telling you the exponentials and natural logs are kind of like inverse functions here, right? And they kind of undo each other. That's a property I need to know. So on the left, I can say, sure, that's just the absolute value of x. But my property looks like this. It doesn't look like e raised to the 1/2 natural log of x is x. I don't know what to do with that 1/2. I got to get it out of there. I also got to deal with the fact that I have a sum in the exponent. And to do both of those things, I'm going to use some exponent and log properties. And these are going to be really important properties we're going to use all semester. You just have to get down cold. So first one, x raised to the a times x raised to the b is x raised to what power? A plus b. Okay? And so in this case, I'm going the other direction. I have the sum in the exponent, but I can rewrite that as e to the 1/2 the natural log of 1 plus 2t times e to the c. Okay? That's one of my important power properties here, exponent properties. I'll write down the other big one for those powers as well. I'll write down this one as x to the a all raised to the b power. What's that guy? A times b there. Okay, that's the other one. Now what? Okay, well, I can take care of this guy now. That's just some new constant. I'll call it c2 because e is a constant and raised to a constant power is also a constant. Right? Nothing's changing in there. There are no variables there. It's just some new constant. But now what do I do with this 1/2? Well, I use another log property. Here's my next log property. R, some number, times the log of a is equal to the log of a to the r power. Okay? That is a property we're going to need. It tells me those factors in front of a log can be rewritten as the power of the argument of the log. So, applying that here, this is e to the natural log of the square root of the absolute value of 1 plus 2t. Okay. But in that way, I was able to get rid of that leading coefficient, that 1/2, and now I just have e to the natural log of something. Now I can think about them as inverses. But I have to clear that number first. So now this is just C2, the square root of the absolute value of 1 plus 2t. Everybody with me so far? All right, 2 more log properties I'm going to write down, because once again, I'm going to give you kind of the complete list over here on the right of things you're really just going to need to be able to recall and use. How about the log of A plus the log of B is equal to the log of AB, product A times B. And the log of A minus the log of B is equal to the log of A over B. Okay. And actually, that last one you can really prove with the 2 previous ahead of it, so it's not really a new one, but you need to know these. So make sure that you get these down. I will give you some support for that as soon as we're done with the warm up as well. Okay, so now we are where we are here. And one thing I can do is I have the absolute value of x on the left-hand side, but I have that constant on the right, so whether it's a plus or minus, I can always swallow up that constant, that sign with that constant, so I really don't need the absolute value over there. And the next thing I'm going to do is evaluate my initial condition here. X of 0 equals 2. So I plug in 2 for x. I have C2 times the square root of the absolute value of 1 plus 2 times 0. Looks like this means that C2 is equal to 2. And now my solution will be 2 times the square root of 1 plus 2t. But I also dropped off my absolute value sign. Why did I do that? All right, here's why. Now, when I look up at that differential equation, I can see right away that I have a domain problem for my t values. What are the domain restrictions for t based on the differential equation? T can't be equal to -1/2, right? That's a power. T can't be equal to -1/2. So if I end up with some function, right? T can't be equal to -1/2. That could look like it's well-defined everywhere, flowing from values that are smaller than 2 to the -1/2 to values that are bigger than 2 to the -1/2. There's a problem. I can't flow right through that gap because my solution is undefined. My differential equation is undefined. Okay? So that's a problem. So instead now that I know that's a problem, I say, well, I could have a solution for the values that are bigger or smaller. I have 2 different intervals in which I can define my solution. Our solution to the differential equation is a function, and a function should be defined in terms of its interval, in terms of its domain. So in this case, I'll be looking for a solution either in the interval from -1/2 to infinity, or from -infinity to -1/2, in one of those two. But if I find a solution in one, it cannot cross over into the other. Does that make sense? Okay, now I have an initial condition, which interval am I working in? Right, that's right, the positive side, right? From -1/2 to positive infinity. In that case, I no longer need absolute values here, because I'm only dealing with positive values of the radical with that domain, right? And so in fact, it's incorrect to include the absolute value signs with my new restricted domain, because really that would be allowing more t values. Can I have solutions with negative t values like -5? Absolutely, because my general solution has absolute value signs in there. In fact, what I did right before we started was I looked at the slope field for our differential equation. I'm just going to plot that guy. Oops, got the scale. Let's just add in here vector scale. Vector scale. Okay. And now I see values of t equals -3 even. And those are a bunch of curves over there. So I have solutions that are defined for those negative t values, but I don't want them here because I'm working on a certain solution interval. Okay? So really, our solution should be defined in terms of an interval where they exist. Any questions about that? Yeah. What's the shortcut to get that arrow I just press the subtraction sign and then the greater than sign, hit a space, and then boom, it'll turn into the fancy. All right. So now, there were a lot of people who had absolute value signs. That's why they were getting things marked wrong in that one. Totally get that. If that's you and you lost points, ask your teacher. I'll give you those points back. Right? It was something that I couldn't really answer via email, that kind of explanation. I'm going to talk about it now. If you lost points for that, go ahead and just ping me and I'll give you those points back. Okay? Any other questions? Yep. No. Yep. That's just it. You separate the variables. You got the integration you got to do, and that one on the left is a partial fractions problem. Now, we talked about for quizzes and exams. Am I going to throw a bunch of nasty intervals on there? No. You want the real sums of partial fractions for a quiz or exam, but you should be able to get through it. It's a good homework problem because it gives you an repetition of doing integration, doing all the algebra. Also, that differential equation is a well-known differential equation called the logistic equation, which is pretty common in C. So it's good workstation there. But it wasn't just the integration was telling me how to do the algebra as well. So that's just good review of the work. Other questions? Okay, let me go through a couple of quick notes and then I'll open up for more questions. Couple things. One, let's go to the course page, home page. Couple things right here. I've added a PDF here. This is an algebra review. It's actually one of the appendices from one of the calculus textbooks, and it's actually really good. It will go through kind of basic arithmetic stuff, have a bunch of practice problems, boiling things out, working with fractions. It will go into more complicated things, common mistakes we make. It will go into polynomial long division, completing the square, quadratic formula. It will get into all the log properties at some point here, working with radicals. These are common mistakes that people made, some of these simplifications, okay? So this is on here. You know, it looks long, but it's not that long. I mean, it's probably like 30 pages. And a lot of it should be easy, right? And some of them go, oh, I've been doing that for a long time, right? So I know a lot of people say, ooh, algebra is really important. Make sure you review it. How do you do that? You go buy a giant algebra book and read it, right? No, this doesn't work. It's a short, condensed algebra review. If you're getting stuff wrong because of algebra, you've got to go through this. You would be amazed at how easy your classes can be good if you are strong in algebra, right? It's just really a big deal. So I would encourage you to use that if you need it. What else? I got a playlist here. So as you can see now, I'm recording the lecture. So I'm recording the screen in my words. Automatically loads to YouTube after the course. I'm dumping them to a playlist. That's how you access the playlist. And we already talked about the video recording stuff last time, so that's on there. One more thing here. If I go to syllabus, we'll see a category called extra credit. That's 2%. So you see the total grade here goes to 102% instead of 100%. There are 2% of extra credit. There will be about 6 assignments throughout the course of the semester will be extra credit. This is the first one, Euler's. Some of you had me before, know I sometimes do this. What is it? It's a one-page bio on Euler. So we get Euler's method, call Euler's method because of the guy and Euler, famous mathematician, like the famous mathematician, one of the greatest of all time, right? And so I just want you to see where this kind of goes. So if you want the extra credit, do a one-page bio. Doesn't have to be source or cited or all kinds of crazy, right? And it's meant for you to take a half hour, jump on the wiki, read the article, maybe follow a link or two, learn some stuff out, get his background real quick, and a couple things you found interesting about it. That's it. It'll be pretty quick and painless, and a nice way to get extra credit. But he really was one of those amazing people of history, so definitely worthwhile. Okay. All right, so I think that was all my big points. The next thing I really want to hit up is other questions. One common thing I saw from a lot of the questions I got with the lab assignments and heard also from my consultants was, Everything's working great with Oilers when I use 20 steps, but then I go to like 2,000 and it's blowing up. And one of the most common reasons is because of those decimals. You have the decimal into your input values, and that tells mathematics not to worry about exact calculations, kills all the fractions and speeds it up like that. And so that is a common mistake. But any other questions? The lab or the homework? There was something that was big fractions? Or was it different here?
It's just like it was coming out and
Overflow error. Now, if it's a decimal issue, you won't get so much an error as it will say the output's too large. When you start using like 100-ish, that could be a different issue. That could be some sort of function. Did it work for 20 though?
it worked perfectly.
Okay. All right, why don't you send me the note at home and take a look at it, okay? Yep.
I had that same problem because the DX didn't change to be different on accident, so like it went from 2,000 to like.
That could be it, right? So that's an issue with saying some values that they want another one that can go up. It's a pretty good balance, right? If one thing doesn't change, it's very easy when you do 2,000 steps for it to go up. So that could be an issue. Like I said, I'll have to look at the code there. Other questions about homework or labs? This morning I had a big list of ask your teacher messages from last night. So I went through all those and answered them this morning. The pre-lecture that was due this morning is not due really. It won't lock you out until Friday. So once again, sorry for posting so late. You get to it totally fine. You don't have to request an extension for that. That one should just let you in until Friday morning. If you need more time past that, go ahead and request an extension then. No other questions? All right, let's make sure I got everything. YouTube playlist, check. Extra credit, yes. Questions, yes. Algebra review, wonderful. And the existence and uniqueness, the existence of solution and solution intervals, we also talked about. So, integrating factors. All right, before we get into that lesson, Calc 1 review, yay! Go ahead and calculate these things. All right, here's my solutions. All right, look at the first one, the derivative of an exponential of something. The idea is in the end, we have that function. The derivative of the exponential is the exponential, right? And the only change, we have this extra function that kicks out. So that's the most important thing. We have the derivative of some function, and the result is that function times an extra piece. And that's kind of a general thing for exponent, or we take the derivative of exponentials. We get that same function plus an extra piece. So that's the verbiage that we're going to use later here. What's the next one? The derivative of the integral. We just get the integrand back, right? So they're kind of not an inverse operation, but kind of feel like that, right? It's one's undoing the other basically here. So the derivative of the integral of a function is just a function. Okay, it's that general point that's the big idea here. And the next one, the derivative of the product rule, right? I don't know what your chant was. My chant was derivative of the first times the second plus the first times the derivative of the second, right? I had to chant that all the time in calculus over and over again like we were, I don't know, in some sort of weird math cult. Okay? But it's important because you really have to have it down. So then I wrote it out generally here. I don't care if you switch the orders and stuff like that. So multiplication, addition is commutative, so you can have different orders. The point is, can you bring it out quickly? All right, so we got those pieces. Now, the idea is that hopefully you had a chance to watch that pre-lecture video. I did get one comment from earlier. Someone said, can you make it bigger because it's so small and hard to see? If you right-click and open up a new tab, then it'll bring you to YouTube, and then you can make it full screen, do whatever you want from there. That's a comment. Okay, method of linear integration, or integrating factors here. What's the big idea? I want this big idea to stick in the head. It's the most important thing. The method of linear equation says you can multiply a differential equation by a special, function in a way that allows you to solve the differential equation by direct integration. Okay? So the whole idea is we have our differential equation and we rewrite it into what I'm going to call standard form. That is what I am calling standard form. It's actually a little bit different than the textbook, which has minus a of t times x. I'd rather use positive. It makes my integrating factor, have a little positive in there as well. That's what I'm calling standard form. Okay. I take my differential equation, and what do? I multiply through the whole thing by my integrating factor. Just multiply the equation by my integrating factor. What do I get? I get integrating factor times the first thing plus integrating factor times the second thing equals integrating factor times the right-hand side. Just multiply it through by integrating factor. Okay? And the idea is that if I chose the integrating factor correctly, then this whole side over here is supposed to equal the derivative of the dependent variable and the integrating factor. That's supposed to always happen. That simplification. Okay? Like, wow, this is a pretty awesome thing here. And I love that because now, if I look at my last equation, I need to solve this thing. Well, I just have the derivative of something on the left. I know how to get rid of a derivative. What do I got to do to it? Integrate. So once I get to that step, we're kind of home free, right? Now I just integrate. Woo! Right, with respect to t. And I get just this on the left. I get some stuff on the right. And when I integrate it, I'll add a constant, solve for x, and you're all done. Integrate. Okay. But the crucial step is taking that sum of these two things, two terms, and recognize the derivative of one product. Okay. Like this must be some magical integrating factor for this thing to work. Well, what does it have to be? Well, if we just look at this piece and say, okay, well, let's do it the other way. Let's actually take the derivative of x times integrating factor. These are both functions of t. So to take that derivative, I'd have to use the product rule, right? If I use the product rule, I take the derivative of the first thing. Oh, that's this guy. That is the derivative of the first thing times the second thing. Oh, yep, there it is. Okay? So this piece is the derivative of the first thing times the second piece. Okay? All right, well, that means that this piece should be the first thing times the derivative of the second. Well, I see the first thing, there's my x, and so it looks like the derivative of the integrating factor is supposed to end up to be the integrating factor times a of t. Okay, as long as that works out, then I'll always be able to do the simplification. Oh, okay, so now I need to figure out what the integrating factor is. Apparently it's something, and when I take the derivative of it, I get the same function back plus an extra piece, right? Now your spider sense should be going off. Like, oh, that sounds like what we just did, right? It's an exponential guy. So that tells me that my integrating factor is going to be e raised to the integral of a of t dt. Okay? That's what IF is. That's what the integrating factor is. Okay? All right. All right, let's see this guy in action now. I got a differential equation. The first thing I'm going to do is find out what that integrating factor is. Okay? First, I got to make sure it's written in this form, my standard form. Is this already written in standard form? It is, right? Standard form means I don't have any coefficient in front of that derivative term, right? There's nothing here. There's nothing out front. That's true over here too. Wonderful. Plus something times x. Okay, I got my x there. Great. So what is my a of t piece then? Just 2, not 2x. I just want the coefficient to the x term here. So it's just 2. So my integrating factor is e raised to the integral of 2 dt. My integrating factor must be e to the 2t. Okay, so I found my integrating factor. Now what do? I multiply through my whole equation by my integrating factor. I get e to the 2t times dx dt plus 2x. Sorry, other order here. Plus e to the 2t times 2x equals e to the 2t times e to the t. I've just multiplied through by my integrating factor. Now, if we've done everything correctly, this should all magically be the same thing as the derivative of my dependent variable times my integrating factor. And then I'll simplify the right-hand side to get that. And then I like to check. I want to check my work to make sure I haven't messed up. Okay? So now I'm going to go over here, myself a little space, and I'm actually going to calculate the derivative of this. In fact, why don't you go ahead and calculate the derivative of that piece, just somewhere off to the side. Derivative of x times e to the 2t. Go ahead and write that guy out for yourself. Please, please, please do. This is one of those weird things, like you really got to write it out and see it for yourself to believe it, right? A lot of people, I'll say it over and over again, they're like, where does this piece come from? That's okay, right? Sometimes you just got to write it out. What do I get here? I get the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. Well, wait a second. This looks exactly like that, okay? And that's the whole idea. How do we go from this step to this step? We're basically doing the product rule backwards, right? It's like the product rule backwards. Any questions so far? Okay. All right. All right, now I got this step. What's my next step? I got the derivative of some stuff on the left and some function on the right. Integrate. I integrate both sides with respect to t in this case, integrate with respect to t. On the left-hand side, I just get this, so I'm integrating a derivative. On the right-hand side, I get 1/3 e to the 3t plus some constant. Make sure you add this on time. Okay. Now what's my next step? Solve for x. I'm going to solve for x by taking everything times e to the negative 2t. If you want to divide by e to the 2t, that's the same thing, same process. Over here, I'm going to get e to the negative 2t times all this stuff, which I can write like that. Or I can write like this. I can distribute that to get 1/3 e to the t plus c1 e to the negative 2t. That would also be okay. Either of these are fine, and there are other forms. Questions? I had lots of questions in my other class. Any questions? Clicker question. Can I do that? A equals yes, B equals no, C equals I'm not sure. No score here. Can I just simplify that last piece, clean things up a bit? Why not? I add that t there. It's not a constant, right? Any constant times a constant, sure, swallow that guy up together. Wonderful. But this is not a constant times a constant. It's a function times that constant. Wonderful. All right. No questions? We will move on. Your turn. There you go. Remember, this is your time here, right? So you get all the homework right now, the homework will be much easier. Right? So take your time, talk to your neighbor, make sure you know how to get through things. Any questions? Ask them now. Ask them now, I just answer them. And you're good. You wait till the homework and you have to stare at it for an hour, right? Careful right away because change all the variables, right? It's not x's and t's anymore. It's y's and x's. That's why you be careful. You gotta be careful, right? Okay. All right, let me get the first couple pieces here. Let's make sure we can go through it and get our integrating factor. First thing is standard form. Like before, we had dx dt equal, or plus a of t times x equals some function of t. Well, now we got new variables. So now we're working with dy dx plus something, some function times y. Y is now our new dependent variable. So that guy's any function of x here, equals some function of x. So we got to be able to change our independent dependent variables. And I know it's annoying and confusing, but it's the reality, right? So that's kind of our new standard form here. So I divide through by x to get dy dx plus 3 over x times y equals x. That's my equation, standard form. This 3 over x is the coefficient to the dependent variable. So now what's my integrating factor? It's going to be e raised to the integral of 3 over x dx. All right, that's e to the, I pull the 3 out. I'm really integrating 1 over x, which means I should get the natural log of x. Oh, wait a second. Now I got 3 times the log again. So this is going to be e to the natural log of x cubed, which is going to be x cubed. X cubed is my integrating factor. So again, I'm referring to that log property again, where that constant out front goes up into the exponent. Yep. Excellent question. Excellent question. I'll hit that up when I'm done here. All right, now I got my integrating factor. Now I take my integrating factor times my differential equation. I get x cubed dy dx plus, when I multiply this by x cubed, I get 3x squared times y equals x to the 4th, multiplied through by x cubed. Okay. Now I recognize, I don't really, but I'm pretending to recognize, that all that stuff is really just the derivative of my dependent variable times my integrating factor. Now, did I recognize that? No, I knew to write down derivative of dependent variable and integrating factor. I knew to do that. Once I write it down, though, I should check, right? I'm thinking the product rule. Now, if I do the product rule, I get derivative of the first thing. Oh, that's right here. Derivative of the first thing times the second thing. Yep, that piece is good. Plus the first thing, y, there's the first thing, times the derivative of the second thing. Derivative of x cubed. Yep, sure enough, it's true. Yay, right? But I am only doing that check. I'm only taking the derivative as a mental check to make sure I'm right. Many students write this expression, derivative of y(x cubed) equals x to the 4th, and then they don't know what to do from here. What's our next step here? Integrate. We integrate this thing. We actually don't do that derivative. I only do that as a check. I integrate this thing with respect to x. Integrate with respect to x. Integral kills the derivative. I got y(x cubed) equals x to the 5th over 5 plus my constant. Now I just solve for y. I divide by x cubed. I get x squared over 5 plus some constant over x cubed. Lots of ways you could write that. This is one of them. Questions? Yep. Excellent question. What happened to the absolute values in the natural log? And the constants is also another good thing here. All right. right, let's see. Let's add them in. Let's add our natural or absolute values back in here. If I keep those all the way through, okay. So the absolute values. In this case, the idea is I probably should keep them through and be a little more careful there. And when I go through and multiply through by the absolute value of x cubed, and I'm multiplying them by other x values, I can maybe think about the positive and negatives there and what I'm going to need. But in the end, what's going to happen is I'm going to have an initial condition. And that's going to let me know where I'm at. Because, is there any restrictions on x based on my differential equation? There are. It can't be 0 because my first step was putting this thing in standard form. And that process involved dividing this equation by x. Okay? So it turns out that x can't be equal to 0. Okay? So that's basically dividing me between positive values and negative values. Okay? So my solution will either be on one side or the other. So I should probably be more careful with my absolute values and keep them in. But in the end, if you give me initial condition, it's either going to be a positive x value or a negative x value. And I'll be restricted to one of those spots. Okay? All right. Now, what about the constant? The constant was also a question. In fact, my next spot back here, tips and tricks, boom, there it is. What about that constant? What about that constant? I really should add it. I really should have a plus c up here. But if I have that plus c up here, well, what will happen? I'll use my property again, and I'll turn it into e to the c over here, which will turn it into some different constant times the absolute value of x cubed, absolute value of x cubed, like that. And then that would be my integrating factor. But what is the next thing that I do with my integrating factor? Not yet. I have my integrating factor multiplied through the whole equation by my integrating factor. And then I could divide through the whole equation by whatever that constant is. Right? Well, I actually don't need it. I can get rid of it. Another way you can think about it is in the book, they'll talk about what goes up in either one. Is up there? The book will say find an antiderivative for that a of t guy. You can use any antiderivative. Right? Or you can use any antiderivative that means that plus c. You can choose any value of c to go in. Right? I will choose c equals 0. Right? That's the easiest one to choose. Okay? But it doesn't matter which one you choose the easy one. Okay? All right, but good question. We always should ask, I skipped something. Am I allowed to skip it or am I not allowed to skip it? All right, any other questions though? All right. All right. Tips, tricks, warnings, all this good stuff here. All right. Some things to think about. One thing, standard form. Make sure you put it in standard form first. One of the common mistakes is not to divide through by whatever factor is in there, and then you get the wrong integrating factor and everything gets screwed up. Make sure you put it in standard form first. Next, continuity of a of t and f of t. After you do that and put it in standard form, you need to check, is there any restrictions on my domain here or here? Just like in the last problem, I had a 1 over x there. X can't be equal to 0. I have to be aware of that. Right? If I have f of t over here, and f of t is the natural log of t, right? There shouldn't be an absolute value in here. When I integrate 1 over t with respect to t, absolutely, I should have the absolute value in there. But if it just gives me a natural log, I can't add 1, in which case the domain would be just restricted to positive values of t. So you just want to check the domain before you kind of start. Next, what if a of t is equal to 0? What would that mean? If a of t was 0, do I still want to use this technique? No, why not? I can just integrate, absolutely. If a of t is 0, this piece goes away, and I'm just looking at the derivative equals some function of t, just integrate, right? What if f of t is equal to 0? Then what? Can I use this technique still? Sure. Do I have to use this technique? Is there another technique I could use? I could separate the variables. I could add this piece to the other side and then just separate the variables because it's already written as a product of t's and x. Okay? So If f of t is 0, you can do it either way. You can do the linear technique here, the integrating factors, or you could separate the variables. So just other things to think about. And we've already talked about the constant piece. All right. So let's go through, do a quick clicker quiz here. I'm going to turn it on, but I want you to go through and answer all of them. Go 1, 2, 3, 4, look at them, just figure out what the integrating factor should be. Write an A, B, C, D, or E next to 1, 2, 3, and 4. And once you're all done with that, then enter in your answer, and then we'll go through them quickly. All right. I only got 1 minute left, so I'm going to go through them. What about this first one? Put in your answer for the first one. All right. Pretty divided between A and B. Once again, standard form. I got to divide through by 2 first. That's my first step. When I divide through by 2, I get y prime plus x times y equals 1/2 cosine of x. That means my coefficient there is just x. So e to the integral of x dx, e to the x squared over 2 should be b. Okay? Make sure you put in standard form first. What about the next one? I'm looking for the coefficient of the dependent variable. The dependent variable is y. There is no y term, right? Really what I would do is subtract that x over here to put it in standard form. The coefficient is 0. Integral of 0 is 0, right? E to the 0 is 1. Go ahead and use this if you want, okay? But it doesn't really do anything, right? It's not really what we would do. If you want to call that the integrating factor, great. What about the next one? What about this one? This one is d. Why is it d? Because of cosine of y. Y is the dependent variable. Cosine of y means that y is now the argument of a nonlinear function, which means this is not a linear differential equation. We use this technique for first order linear differential equations. So the first question at pre-lecture was something like this, and one of them had sine of t, one of them had sine of x. That was the difference, right? We got to make sure it's a first order linear differential equation before we use this technique. And the last one is just that guy. So we have e to the integral of 2x dx. That's going to be e to the x squared. All right, for next time, we're going to do a little bit on green functions. Then we're going to have a quiz. Basically, I will have the whole order from 1.4 be mostly earlier stuff, but a little bit from